that we did not finish last week. Now we introduced to you the model about a DC motor. Okay. Now so far we introduced to you two kinds of model. One is superficially excited model. The second one we have the shunt connecting model. And the last one we introduced to you here, it is so-called a series motor. Okay. Now the meaning of series motor is that you can find in the picture we saw here, we now have a single voltage, VA. The single voltage, we supply it to both the field at the stator and also the armature. Okay, armature means the motor. And this field and armature are connected in series. Therefore, we have a name so-called a series motor. Okay. Now remember last time we told you we have the shunt motor that the field and also the armature are connecting in parallel. Okay. And now we connect them in series. Okay. Now we also work out some equation and you can find that firstly, the magnetic flux found equal to Ks times Ia. Okay. Now this formula actually comes from the equation that lambda means the magnetic flux linkage, which is equal to N times lambda. Lambda means, sorry, not lambda, phi. Phi means the magnetic flux. Okay. This is the magnetic flux. Now, by our formula, we told you before, N times phi basically equal to L times I. And therefore, if you rearrange the formula, you can easily find an equation phi equal to L over N times I. And therefore, we call L over N as our Ks. And immediately you get this formula. Okay? And now, previously, we introduced to you the induced voltage equal to Ka omega M phi. And phi equal to Ks times Ia. Therefore, we replace phi with Ksia in this formula. And we can further combine them into a constant K. So your formula will become K times omega M Ia. Okay? Now similarly, for the torque equation, you can substitute phi equal to Ks times Ia. Okay? Now this form, actually the first equation we told you phi equal to Ksia. That means when you increase in current, the magnetic flux will also be increased for series motor. And now for the torque, you can substitute phi equal to Ksia. Therefore, at the end you have the formula T equal to Ks, Ka Ksia squared. Okay? And now if you apply KVL to the model, okay, KVL, you can easily develop an equation VA equal to, now if the current is I times RA plus EB. Okay? Now sometimes you may find we have an input resistance for the motor. It is so-called Rs. And this Rs can be added with Ra to form the total resistance of the motor. So, and you can substitute EB by Ka omega M Ksia. So you can get this formula Vs equal to Ka omega M Ks plus RT times Ia. Okay? Now for this formula, you can rearrange. You have Ia equal to Vs over Ka Ks omega M plus RT. And you can use this formula Ia in terms of something to be substituted into the torque equation. So at the end you get this formula. Now, if you look at this equation very carefully, this is what we call the torque speed curve for a motor. Okay, remember, for every motor, we look for the torque and omega relationship. So this formula tells you the torque and angular velocity relationship for the series motor, where T equal to KAKS times Vs square over Ka omega m Ks plus RT square. Now you can get T relating to Km, omega m here. Okay? Now therefore in your mechanical design, you may make use of this formula. Okay? And you can look at the characteristic of the series motor that now for the series motor, we saw the characteristic in blue. You find that when power is increased, at the beginning, the torque of the series motor come up with a small magnitude. But after certain values, you find that the torque increase, not this one, increase and increase. That means the rate of increase for the torque increasing is increased. The torque become larger if you supply a high power. Okay. Now on the other hand, if you look at the power speed curve, you find that when the power is increased, the speed of the motor, series motor, decrease. Okay, it becomes the rotation speed become less and less. So that if you say you are using the series motor in a speed regulation, it is not good because it is not a constant. It is decreasing when you increase the power. Okay. Now we sum up the DC motor to you. Now we have two DC motor we give you here. Now firstly, for the shunt motor, we found that the field is connecting in parallel with the armature, and it can provide a constant voltage and field excitation. Therefore, the motor we have just shown you, it has a very good speed regulation. Now, on the other hand, for the series motor, you find the field winding is in series connection with the armature. This motor has a very high starting torque, but poor speed regulation. Therefore, if you are going to use the series motor, you may consider that the application may have something require low speed and high torque application. Okay, for example, the lift, the motor for a lift, you may consider low speed and high torque for the application. Okay. Now, any questions so far? Now we give you an example about the shunt motor. Now, in this example, we try to find the speed and torque for a 4-pole DC shunt motor. Now to solve this kind of problem, before you do anything, I suggest you to draw a model to describe the motor. Okay. Now, because it is a shunt motor, therefore the field, which consists of a the field resistance, RF only, it is in parallel connection with the armature. The armature has two parts: the armature resistance, RA, and also a back EMF, EB. Sometimes we got a input resistance, RS. Now this is the input voltage, Vs. Okay. Now this is the model we look for the shunt motor. We always draw it out in order to let you know what happened inside. Now in this problem, we are looking for omega m and torque, and we give you some parameters for the motor. It is a 3 HP, 240 volt, 120 rotation per minute. We have the circuit parameters, IS, that means the input current, equal to 30 amp. The field current, IF, equal to 1.4 amp. RA equal to 0.6 ohm. The magnetic flux equal to 20 milliweber. N equal to 1000, M equal to 4. Okay, now firstly we make a calculation on the SR, on the power for the SR unit. Okay, and do you know what is HP? Do you know? Health point? You are playing game, right? Horsepower, right? Horsepower, 3匹, okay? 3 HP means 3匹, okay? And 1 HP means 746 watts. Therefore, we multiply the power by 3. You get 2238 watts. Okay? And now, if we apply KCL at this loop, okay, we get IA, the armature current, equal to IS minus IF. So it gives you 28.6 ampere. Okay? Now in this example, we assume our RS equal to 0. So it does not have any potential drop. But some of the example we have RS. And in our tutorial worksheet, we will show you an example that we have RS. Okay? So if you apply KVL to this path, you have Vs equal to IARA plus EB. So your EB will become Vs minus IARA, and it gives you 222.84 volts. Okay, this is EB, the back EMF. Now after you get EB, remember that you have the formula EB equal to KA find omega m. So this formula seems that it can help you to find omega m. And the problem is that what is the value of Ka? Okay? And now in the question, in this solution, we help you to compute Ka by using another formula we provide you. This is equal to Pn over 2 pi m. So the motor is a 4-pole motor, therefore P equal to 4, N equal to 1000, M equal to 4. Now they are the coil geometry in the motor. Okay, we substitute them into the formula. We get Ka equal to 159.15 volt second over Weber radian. This is the unit. Seems that it is complicated, but you only needed to using EB, the unit is V, magnetic flux, the unit is Weber, omega m, the unit is radian per second. You can know the unit for Ka, volt second over Weber radian. Okay, you can try to work out the unit by yourself. Now you can find omega m. You're using EA over Ka find. At the end, it is equal to 70 radian per second. And after you get omega m, you can get the torque because it is equal to the power over omega m. And it gives you 32 Newton meter. Okay? Any question? Now actually, you may find we only using the equation or apply the equation to solve the problem. For this kind of question, we always do that. Okay? Now, the last example, it is relating to series motor. Now in this example, we are going to find again the torque. Okay? Developed by the DC series motor when the current supplied to the motor is 60 amp. Now, again, before we do anything, we can draw the motor. It consists of the field, RF, in series connection with the armature. That is, we have RA together with the back EMF, EB. And we have the input voltage, Vs. Okay? Now, we are going to find the torque at 60 amp And we give you some of the parameter for the series motor. It is 10 HP, 115 volt, full speed is 1800 rotation per minute, and the current equal to 40 amp. Okay, now these two conditions are relating, so that when you give 40 ampere to the motor can rotate at 1800 rotation per minute. Okay, and now we work out the solution. Now, firstly, we already told you that the magnetic flux equal to KSIA, and now the rotation, the number of rotation per minute is 1800, and we first convert it into angular velocity by multiplying 2 pi over 60. It gives you 60 pi radian per second. Power equal to 10 HP, so it is equal to 7,460 watts. From this equation, you can get the torque. Okay, T40M, the power over omega m. So it gives you 39.85 Newton meter. Okay, now but we already showed you that the torque can be computed by another formula given by KAKS times IA squared. Or we group KAKS into a single constant equal to K. So it is directly relating to IA squared. And we substitute 40A in 40 equal to IA, and torque equal to 39.858. So your constant K is given by 0.0247 Newton meter per ampere square. And we assume the constant K is not changed when we increase the current to 60 ampere. So you're using this K again at 60 ampere. And now we multiplying I squared, which IA equal to 60. At the end, we find the torque, which is equal to 88.92 Newton meter. Okay? And now we finish our chapter 6. Do you get any questions?